Okay, I'm John Cosmas from Brunel University, and I was the technical leader of a European research project called Internet of Radio Light, and its aim was to produce radio communications access points consisting of combined visible light communication and millimeter wave multi-component carrier architecture, and to see how it performed in the field. The this we the, the project completed the construction of the system and successfully conducted performance tests in the building research establishment, Integer House Lab. It's a lab that consists of a home that's used for testing new technologies. And the objective of the trial in this home was to test coverage, latency, location accuracy, and electromagnetic exposure performance of both the millimeter wave and the visible light parts of the system, and to provide recommendations for improving the design and produce design guidelines for optimal deployment of the 5G remote radio light heads in the buildings. It therefore helps to solve the problem of broadband wireless access in buildings and promote the 5G standard. This is a picture of the integer home in the building research establishment, and we were on the first floor. And so we were testing, mainly we were testing audio video streaming to ultra high definition TV service. And this was the concept of the system. It's we aim to provide a 10 gigabit per second Ethernet ring to light access points, which provide a 5G signal to support visible light and millimeter wave access points. And this most of the aim was also in order to keep the footprint of the electronics small, to put most of the signal processing in the what we call the intelligent home IP gateway access point. This is the architecture that transpired from that. You can see the 10 gigabit per second Ethernet ring. You can see the RAN split between the upper layer processing and the lower layer processing. You can see the millimeter wave and VLC modules. You can see the layer 2 processing here, and you can see the OpenStack intelligent home IP gateway server here with the multi-source streaming, location, security, and transcoding virtual network functions, and the OpenFlow switch operating, and their interfaces to the internet and the 5G network. In order to, one of the main aspects of the system was that it could provide location data. So we achieved this by using a splitter, so that the splitter sends the same IF signal to 4 remote visible light access points, and that we can use a switch within that system to switch between each of them, so that we can measure received signal strength data from the user terminals. And similarly, for the millimeter wave, we will have a switch here that selectively chooses one of 4 millimeter wave access points, so that we can measure the time difference of arrival from each of the remote radio light head access points. So here's the setup with the frame. You can see that the switch. This is a subframe for a 5G, and you can see that for OFDM symbols 11, 12, 13, and 14, we selectively switch between the 4 lights so that the user terminals only receive from OFDM symbol 11 from one of the lights, and therefore it can obtain receive signal strength data from that, and by triangulation be able to obtain its position. Similarly, for the millimeter wave, we send a pseudo-random noise sequence on the 14th symbol of a particular OFDM frame, and that is sent to just one of the radio lighthead receivers, millimeter wave receivers at a time in each of these first four slots, and that's used to obtain the time difference of arrival information in order to obtain location information from the devices. This is all represented in this system here. Each of the RAN, the user equipment reports its received signal strength data to a location database. The RAN reports its time difference of arrival data to the location database, which the location server accesses and produces user equipment location information at this point here using this algorithm here. I presume these slides will all be made available to the delegates so that they can look at the detail of what I've written on the slides in their own time. Okay, so that's the architecture in brief. So here is the integer home first floor layout. It consisted of a sitting room area, a kitchen area, and an entrance hall area, and a conservatory area. And, here is Kareem, one of our research assistants, on the RV user terminal, taking a millimeter wave measurement from the. In here you can see the 4 remote radio lighthead system, and in the background you can see the layer 2 processors and the OpenStack server. So we took measurements at ground level, but also we took measurements at tabletop level. Here you can see Ben and Kareem. Ben is now using a visible light communication receiver to measure the location accuracy, and Kareem is recording the measurement. Here you can see the remote radio lighthead. In the middle is the communication LEDs, and the outside are the illumination LEDs. And in these corners here, this is supposed to be the millimeter wave antenna, but we located them outside of this access point because we wanted to experiment with them by angling them at different angles. Here you can see a close-up of 2 views of the antenna, side view and front view. The antenna has been made, a cheap version of the antenna, made out of PCBs in order to make it like a consumer product. What we found was that we needed to angle the receiver towards the transmitter, both for the VLC and the millimeter wave measurements, in order to get better results. And so we quickly 3D printed a 2 degrees of freedom gimbal in order to be able to hold the measurement point steady while making the measurement. And we adapted it so that it could also be used for the millimeter wave antenna. And we also made a little 3D printing so that we could angle the antenna at 0 degrees, 30 degrees, 40 degrees from the vertical. This is the front end of the VRV test terminal user interface, where you can see the amplitude phase diagram here, the power delay profile and the EVM evolution with time. These are the parameters of the transmission system. The millimeter wave required 3.5 gigahertz IF signal, and we were operating at 40 gigahertz. And the visible light required a 15 megahertz IF signal, and we were operating with the visible light spectrum. And we'll be using 64 QAM for millimeter wave and QPSK for VLC. We originally had intended to use 60 gigahertz, but because the components from the US were very expensive and being delayed for the delivery, we switched to a 40 gigahertz system. But the whole concept of the system was that it would be all operating in license-free spectrum, so that nobody had to ask anybody for permission to operate it. So this is what we obtained for the visible light coverage with the light, communication LED pointing straight down, and the receiving photodiodes pointing straight up. It had about 0.6 meter diameter coverage. Its maximum propagation distance was 2 meters, and this limited coverage is attributed to the physical construction of the photodiode sensor housing. So once we built the system to angle the receiver, we obtained a better diameter, which was a 1 meter. We continued to have a 2 meter propagation distance, and the variation of performance between the 4 light heads was attributed to the variability of the transmitted light intensities, which we couldn't change without a special tool from our colleagues in China, which we didn't get in time, so we weren't able to modify these. But we can imagine that they would have the same performance once we increased the intensity of the light. This was the coverage area and measurement map we used for measuring the location accuracy. So we took some measurements of location accuracy where we angled the photodiode receiver towards the LED transmitter for each of the measurement points. And we sent this information to our colleagues in Paris who used an artificial intelligence software to work out the optimum position of the anchor points in order to minimize the errors of the difference. And the results were that we were able to get the smallest location error of 0.55 centimeters, the average location error of 5.28 centimeters, and the highest location error of 11.9 centimeters, with 80% of all the location measurements below 10 centimeters. This is the measurement grid that we use for millimeter measurements, and we first of all pointed the transmit antenna vertically down, and the receive antenna vertically up, and we made measurements at 0.7 meters above the ground with the receiver angled and not angled, and we saw a slight improvement of results when angling the receiver antenna towards the transmitter antenna. And the asymmetry of performance was attributed to a glass door on one side of the coverage area, which produced the millimeter wave reflections that impaired the performance of the receiver. And we did this at also 0 meters above the ground, and so with and without angling the receiver antenna towards the transmitter antenna. And we noticed that the performance at 0.7 meters was better than at 0 meters, because the table shields the reflections from the floor, thereby getting better performance in this setup than it is in this setup. Yeah, so after we did the visible light measurements, we moved on to the millimeter wave measurements, where we pointed the antenna straight up without angling and with angling. This is a floor. I can't see what the title is. Yeah, this is pointing 30 degrees from the vertical, and with and without a receiver angling. So this is angled and this is without angled. And we saw that angling the this is receiver non-angled. This is receiver angle. We found that angling the receiver improved performance. But we also found that there were variations during the day, so that we couldn't explain. And this is from the measurements that we obtained at 0.7 meters on the tabletop, with and without a receiver angling. And you can see that with angling, we obtained pretty good results. The reason why we stopped at 2 meters is because the synchronization cable was not long enough, but we expected this to be able to continue on for about 6 meters. And the performance of the millimeter wave does improve with the receiver angling towards the transmitter antenna, and it improves near the location of the transmitter antenna with backscatter. So you can see here that this is the position of the transmitter, and there's a certain amount of backscatter that also exists. So the antenna doesn't have to be placed right against the side of the wall. The performance of the millimeter wave antenna does improve a little bit with 40 degrees angling from the vertical, but not as much as the 30 degrees angling. So what we can say is that we obtained 42 megabits per second VLC system with a 10 megahertz bandwidth for 4-QAM and subcarrier distance of 30 kilohertz on the VRV test bed. We had a coverage of about 1 meter by 1 meter. The average location accuracy was around 5 centimeters. With a millimeter wave, we got a maximum bit rate of 310 megabits per second, 64 QAM and subcarrier spacing in the VRV test bed. And the Brunel test bed, we got a 70 megabits per second on 100 megahertz bandwidth using 4 QAM subcarrier spacing of 30 kilohertz. And the millimeter wave coverage area was around, probably around 2 meters by 6 meters. We got also measured 0.5 milliseconds latency between the user terminal and the external point of the RAN operating at 10 megahertz bandwidth. The remote radio light head and DRAM controller designs could be enhanced to operate at 400 megahertz there and 64 QAM, thereby producing something like 1 gigabit per second per room. This is a scalable system, and so we can go up to 32 remote radio light heads with one gig for each of the rooms, up to 10 gigs as a total. We also performed field strength measurements, and this was done by the Building Research Establishment, and they first used FICO and WinProp simulation tools to estimate the extent of the electromagnetic radiation within the room and its effect on humans. And then they went into the room and took these measurements using these very well known state-of-the-art EMF safety measurement devices. And we found that in the end, the results were well below what the safety measurements required. So we were very happy with that. So the VLC conclusions is the current system capabilities are suited to personal area networks, e.g. trains and planes. The maximum bandwidth needs to be able to increase from 10 10 megahertz and 42-bit megabits per second by a factor of 10 to make it a viable competitor for millimeter waves in home. The maximum distance needs to increase by from 2 meters by a factor of at least 2 or 4 to 4 or 8 meters. The maximum aperture angle needs to increase from 60 degrees to 120 degrees. The maximum aperture angle of the photodiode also needs to be more like have the characteristic of a fly's eye, so that it can have multiple receptors pointing at different directions, thus providing a broad range of field of vision. And a Fresnel lens could be used for that. And location accuracy were maintained by manually switching between the communication LEDs. This needs to be autonomously rated. A millimeter wave system, we need a minimum of 4 of these, and access points can provide a coverage of a sitting room area, 4 meters by 6 meters. The latency is 0.5 milliseconds. The measurement campaigns need to be performed on circular and dual vertical or horizontal polarized antennas. The uplink was not integrated on the VRV Brunel test bed, but we managed to get it working in the Brunel test bed, which paves the way for time difference of arrival measurement tests. The location of the 4 millimeter wave antennas do not necessarily need to be integrated with the lighting system, as their transmission propagation properties are quite different. And the best location of the 4 millimeter wave antennas is in the 4 corners of the room. And then further experiments need to be performed for the 4 transmit antennas to show that this man-made multipath environment does away with the requirement of angling the receive antenna towards any one of the transmit antennas. The exposure conclusions can be summarized by saying that they're well within the recommendations from the ICN-IRP exposure limits that they have recommended for sustaining human health. This project was funded by the European project. Thank you very much. And there is a video here. I'll leave the link with you. So the video shows us working in the building research.